Exercise 123. So this is a following up of last exercise. So let's recall that in the last exercise we have discussed the obstruction of an extension being split. Let's quickly recall. So this is continue 122. So recall that for a given extension of A by B, so this is surjective sequence. This induces surjective sequence by the fact that the derived functor is a delta functor. We got B, E, A, extra B, and then we define this partial identity of A to be called the obstruction of this C being split, because as we proved, is equal to 0 implied that C split. This is what we have done. Exercise 122. More, we have proved that we call this of C. So this depends only on the equivalence class of C. The equivalence class as extension of A by B. Okay, so one thing we haven't answered but is very natural is what's the relation between this extension 1AB and the extension class of AB. So this is our exercise today. So let's work in the category R modules. Given two modules A and B, the mapping I've described from the extension class to its obstruction actually establishes a one-to-one correspondence. Equivalence classes of extensions of A by B to the extra one group of AB. In which the split extension corresponds to 0 element in this external group. Proof. So what we do is that we construct a map at the beginning using the fact that our modules have enough projectives. And the reason we do that is that because projective modules, let's say projective module, and then we have home and comma slash is exact factor, right? That's what we know. So let me write down for any shortly that sequence there exists someone zero to n p a to 0. So we require this a is a given a, and this we require this to be projective. This exists, and you just take this to be kernel, right? Then we apply this control variant factor home comma slash comma b. This gives home a b, home pb, home mb, and then extra 1 AB, and extra 1 PB, but this will be 0 because so we have done exercise before when this, or at least we have mentioned that, and sub exercise telling you that when P is projective, then home P is exact, and so its corresponding homology would be acyclic. Should be 121, I guess. That's why we picked that P to be projective. So let's concentrate. We don't really care those terms. Let's concentrate here. Sorry, this is AB. So we want to construct a map from extension class to external AB. And now we have this surjective map. What we have to do is that we're going to prove that claimed map actually I don't know how to pronounce that map. So this H from from identity of A from extension to its obstruction. Let me check how do I pronounce this Greek word. So this is actually theta. Yeah, this is theta, although it's the capital theta. So this is theta. So we're going to show that firstly theta is surjective. Which means that for any x in this extra class, there exists some c such that partial identity of A equals X. The same is nothing to do with C, but as we show that this partial is comes from, so this partial is related with that short exact sequence, so better write this way. Okay, so let's do this. So firstly, so this partial is not that partial, this is a partial, so comes from this short exact sequence, and then there is some beta map to X. This beta is telling you that you have a map from M to B, and then I'm going to construct the extension such that from that extension we apply a delta functor got the line exact sequence, the partial identity of A with respect to that short exact sequence is exactly this X. Let me write it down. So I'm going to construct first the extension and claim that the obstruction of this extension is X. So the extension I'm going to construct it as follows. So I'm using this beta, and then I define this extension E to be the push out of this J and beta, and then by the universal property of push out, if I define a map of A from B to A by 0, then by the universal property of E, because J, let's call this sigma, J sigma A, wait, so here I put identity, wait for, wait, what I want to say, I want to use the universal property of push out E to construct a map from E to A, because I'm going to look at firstly from M to P to A, which gives you 0, and secondly from M to B to A, I define to be 0, and so there is commutative diagram making this commutative, right? But then this commutative diagram telling you that this is surjective. And we just don't know this is the kernel or not. But by the fact that you have a push out of our modules, when this is injective, then it implies this is also injective. So maybe I will discuss this as some exercise. It's just by computation. And then question is this exact sequence as the kernel this equals the image of this. So the composition is 0, telling you that the image is contained in the kernel. Right. So let me call this pi prime. So this is actually kernel pi. And so this B is contained in the kernel of pi prime. I guess by precise computation, one could show that this is indeed the kernel. I mean, in this particular case for our modules. Let me try to see whether I can explain this clearly. So this E is just B. There's some with P, quotient by the relation beta minus J of M. I want to use the universal property to describe this pi prime and compute this kernel precisely to see exactly those B. So maybe the first thing, let me put this sub-exercises to explain why this is injective. Okay, so this is because we have this injective map here. So sub-exercise 1, this implies Let's give it a name, call this J, beta, I, sigma. So J is injective, implies I is injective. This is a very general situation. I'm just using the symbol of our situation, but this works for any R module. And second exercise will be saying that surjective implies surjective. So let's prove this. As I said, recall that by the definition of pushout, this is a pushout. E is isomorphic as R module to bijection with P quotient by beta minus J. And so we know that this I and sigma is defined as B is mapped to B, 0, and then X is mapped 0x. So this is exactly E is making this diagram commute by its definition, because when elements comes from M, here is arrived at J of M, and here is arrived as beta of M, and so beta M 0 equals 0 J of M, because beta M minus Gm, their difference is 0 in this module E. And so if B0 is 0 in the quotient in E, then this implies B0 equals sum of beta of M minus J of M, but J is injective. M is 0, and so this implies B equals beta of M equals beta of 0 is 0. So this is injective. One could prove the surjective correspondingly. So now suppose you have an element, let's say BP mapped to 0 in A by pi prime, question is that there exists some element B prime mapped to this B gamma P, we have to translate this condition more precisely, because we know that image of B is just B prime 0, so we have to show that if BP is mapped to 0 under pi prime, then P must be 0 and B is in B. but I don't know this is a trick or not. This is actually pi prime of b0 plus 0p, right? But pi prime of b0 is always 0. This is just the same as 0p. But if you have pi prime 0p equals 0, then this is saying that, look at the community diagram, p is mapped 0p, and then pi map it to a. This is mapped to 0, then it, by the commutative diagram, this is telling that this must be 0. If this is mapping to 0, this tells you that this p is in the image of j. Alright, there is some jm equals p. Once this is the jm of p, this implies that this 0 jm, but then jm is the same as minus I of some b prime. Sorry, it's the same as minus, it's the same minus beta of n 0. And so this is telling you that this b of p equals b0 plus minus bn. 0 is again something in b0. This proves that current pi prime is contained in b, and so this is equality. So we have this shortly as equals. Okay, so let me copy it here. This is the exact sequence. Let me call this C, and let me show that this is X, because so let's apply the delta functor. By delta functor property, we have this home A, B, home P, B, home M, B, X star 1, A, B, and then 0. And so we also have this map. So here to home, oh wait, because this is a contravariant functor, this direction should be reversed. EB and then BB X star 1 AB, right. And this map is exactly mapping this identity by composition with beta. But this beta is, by our definition, corresponds to this X, and this is exactly telling you that identity is mapped to under this partial to X, because this vertical map again comes from identity of A, so in some sense this is identity, or at least isomorphic. And so you could think of it, this is mapped to X. And so we have proved that X is actually partial of identity B. So what I'm thinking is that I'm hesitating that. So last exercise we defined to be home AA, we're using the covariant functor home A comma slash, but I think there should be no big problem with that. Yeah. Which means that this sequence split dependently if this is 0, right? Yeah, this is just, that is split from this position, this just split from this position, so it's equivalent actually. Yeah. Now let's show that we can construct a map from reverse the direction from X star AB, this group, to the set of equivalence classes of extensions of A by B. So this is a little tricky. What we are going to do is that let's start with extension, let's say X. We're going to map it to equivalence class of extension of A by B. This class is the one we just called C. We constructed by pushout, but this is not yet finished because you have to check this is well defined. Because how did you do that? Recall that from X we choose one lift that is mapped to X under that arrow here. Where? Here. Here. Right, so there could be, for example, beta prime mapped to the same element X. In that case, you would imagine, just follow the same procedure, you would construct some, let's say E prime. And basically, to show this is well defined, you have to show that there exists actually isomorphism. This is what we are going to do, okay? This is a little technical, so let's do that. The observation is that suppose we have beta prime. Let's back to here. You have a beta prime, then notice this is mapped to 0, and so this for into the kernel partial, and so there exists some map from P to B. Let's call it F, that is mapped to beta minus beta prime. And now let's look at our Schrödinger sequence. This is A, this is projective. We first, by push out, define this E, and then prove this Schrödinger sequence. And then we're going to construct a map from, let's put this identity, call this I, call this sigma, call this J. I'm going to construct a map from E to E prime. how I'm going to construct this map. Let me call this I prime. I prime is the one. For the similar procedure, you could use beta prime to define a map I prime and then form this short exact sequence. Still push out. This is how we define E prime. Right, we have E, I, E prime, I prime. Now we're going to relate this E and E prime by first put I prime here, and I want to use universal property of push out to construct a map from here to here. So how do I do that? I'm going to put some map here to make this diagram commute, and so by the universal property force there to give this map. So what I'm going to put here is, to make the diagram commute, what should we put here, right? So the question is, what composed with J will give you I prime composed with beta? What we know is that I prime from here, what we know is that I prime beta prime is, let's call this theta prime. Theta prime composed J. And so it tells me that I prime beta is I prime beta prime plus I prime beta minus beta prime, and so this is I prime beta prime plus I prime. Recall that beta minus beta prime is our F. Our F in the kernel from P to B. So this is our F. And so we find what it is. So by this is theta prime J plus I prime prime. Sorry, so a small mistake I made is that, so this is telling you F is mapped. So this map is, you have M to P and then you have some P to B, call it F, and this composition is F composed J. And so this is telling you Fj equals B minus B prime. This is Fj. So this is IFJ. So this is finally telling you sigma prime plus I prime F of J. So what we put here is just sigma prime plus I prime F. Making this diagram commute, let me call this G. And so this G satisfies making the diagram commute, in particular J I equals I prime. And then we have this commutative diagram, J sigma equals sigma prime plus I prime F. So we constructed this map. Similarly, you could imagine that we could construct another map from E prime to E. So here we put I, E prime to E. You could imagine here we will put, for just the same argument, we would put, instead of sigma prime plus I prime F, this would be sigma minus IFF. And then there is this map, let's call it H. So let's subtract these two parts. We have this H satisfies I prime equals I, and then H sigma prime equals sigma minus IF. Now we claim that we have constructed a map. We claim that the two constructed map from E prime to E and E to E prime isomorphism. So this direction we have H, this direction we have let me put it here continuously. This direction we have J. So we have sigma prime here. So let's say, actually, we only have to check that. This composition is again sigma prime. Then by the universal property, this will force is H compose H. This will force G compose H to be identity. Because this is the universal object, and you have construct two maps. The first is just through beta prime, I prime, and J sigma prime. The second is, let me resay that. This is a universal object. Then for any object satisfying the commutative diagram, there should exist a unique map from this to this. In particular, from E prime to E prime. If I could prove, so this is totally identity, so the composition is again beta prime. So you have beta prime. If I could prove the composition, this is sigma prime, then the satisfying commutative diagram, and so by the universal property, there is a unique map from E prime to E prime. But this unique map must be the identity, because identity makes it works. But on the other hand, you also have this composition of J and H. This will tell you that J compose H is identity. And similarly, you could have H compose J is also identity. What these two put together will tell you this isomorphic. Okay, so the question or left to check is why J compose H compose sigma prime equals sigma prime. This will comes from those computation we have done here. Let's just check it. So J compose H compose sigma prime would be firstly J compose sigma minus IF. And so this is J sigma JIF. J sigma JIF, what is that? J sigma JIF is sigma prime I prime F. Let me recall. Sigma prime I prime F minus JIF I prime F. This is exactly sigma prime. And so we are done. Okay, so what are we left to do? We've constructed a map on both sides. We proved the first direction is surjective. So we're only left to check C, theta equals identity. Over extensions. Of A by B, right? This is the only thing left to check. So let me give a sketching of this part. So given extension C again of A by B, then the lifting property of the projective module P gives a map. So let's say we have this C, B, X, A. Then this is a surjective map. P maps to this surjective map and then factorize by the universal property of P. Let's call this tau. And now left-hand exercise, sub-exercise to check. The x is actually, so again, this you see the map here. X is the pushout, again the pushout of J and let's call this gamma. And this would then tell you that the way this would tell you that theta of this C apply C equals C. So why this is the case? Why this is C? So this is recall this is defined to be partial identity of A or partial identity of B, depends on you use which controller and the covariant factor. Right? And then we apply C. It's just telling you that always based on this fixed at the beginning short exact sequence, and then we use that to construct things, right? And of course we're always showing that is well defined, independent of the choice in some sense. This C comes from the pushout. This is exactly telling us this C of this comes back to C. Actually, it is home AB, home PB, and then home MB, extra one AB, right? For any given class here, we're going to construct an equivalence. By taking any preimage of this and then construct the equivalence by pushout. Actually, in our case, this gamma should be mapped to this. Why this gamma should be mapped to this? This is because exactly what we have proved at the beginning. You apply the delta factor to those. So what we got is here. So let me think. We're applying this home bar B. If I home bar B, then this should in reverse condition. This is home B B extra one AB, Exactly, this is mapping this identity of B to this partial identity B is exactly this partial of gamma, and so which means gamma is exactly a preimage of HC. And so we prove that actually this holds, and we're done.